Hey everybody. So I was expecting we were going to have another 2 to 3 weeks at least for lessons before we reach the end of the year. But you might have seen Mr. Wilson's his email, I think is what he was doing, that he sent out this last weekend saying that our lessons are actually only going to continue through the end of this week. And then we'll have some time to finish up projects, to take our final, and just wrap up the year. Because we're not meeting in person, we're going to have more time to give you to catch up if you're behind. And I know a lot of you, for different reasons, in my class and in your other classes, have fallen behind. So hopefully that time will be put to good use by you. So what we're going to do today is something called Trig Identities. This is how I'm going to finish out the year. This is one of my favorite topics in all of math. So before we can teach you about trig identities, though, we have to go and complete our knowledge of what the trig functions are. So you are very familiar with SOHCAHTOA. We've been doing it since, well, at least last year, maybe your freshman year, I don't remember. But sine, cosine, and tangent and their definitions. What we have not spent time teaching you, because for whatever reason it's just how CPM arranges their book, is the cosecant, secant, and cotangent function. So these are three more functions that, if you look closely, actually mirror your sine, cosine, tangent very, very closely. So, for example, on your sine, you see that that is the opposite over hypotenuse. Cosecant is the hypotenuse over opposite. So technically they use the same things, and I could in fact write this as the sine of theta is 1 over the cosecant, or that the cosecant is the same as 1 over the sine, because either way it takes what the sine is equal to and flips it upside down, or takes what the cosecant is equal to and flips it upside down. And I can see that that relationship exists between these pairs. Now, one of the worst things to do is just going to be to remember what goes with what. But you will be allowed to use whatever references you'd like, and in fact, I recommend that you take notes on this, and I'll also show you a document that you could use on your final, which, even though we just barely took your midterm, I am still going to give you a final where I'm just going to add this information to that final. I apologize that they're so close together. I did not intend for that to happen at all. I thought we would have a few weeks between them. Okay. So these right here are the first of your identities. Identities are even stronger than equations. They're more like definitions. Definitions and relationships. So these are called your reciprocal identities. We're going to definitely be using these later. So again, you can write these down. I'll give you a PDF that you can use. Okay, I want to go through one more set of identities, and they're called, oh, actually I wanted to go through two more sets. Let's do the quotient. Now it'll be quick. Alright, so we know, for example, that your tangent function is equal to your opposite over your adjacent, right? Now, what we've not played with necessarily is how it is defined in terms of just trig functions and not side lengths. So, two ways I can play with this. First of all, I'm going to pick two trig functions that one trig function that uses opposite and another thing, and then one that uses adjacent and the same other thing that the sine used, or that the opposite used. Kind of gave it away. So what I'm going to do is I'm actually going to write sine over cosine. And I'm going to show that this is true. Right now I'm not sure if it's true, but I know that my sine is my opposite over my hypotenuse. My cosine is my adjacent over my hypotenuse. And if I use my rules of fractions, and you got to think about my little sister as you do it, then my hypotenuses cancel and I'm left with opposite over adjacent. So your first quotient identity is just that tangent of theta is equal to sine of theta over cosine of theta. And since cotangent and tangent are the same thing but one's upside down from the other, your other quotient identity is that cotangent is equal to cosine over sine. Okay, this right up here was just a proof. Okay, so that's two sets of identities. The third one's my favorite, and honestly, you're going to use all three of these in so many places. But the third one that we're going to teach you is called, or are called, the third set, because there are three of them, is the Pythagorean Identities. So, for proof first, and then we'll show you what the identities themselves are. Let's say you have a right triangle. I'm not in love with that right triangle. I'm going to try to make it look a little bit more like the one on the unit circle, just because there was something about what we taught you on the unit circle that we care about. And that was that we were using a hypotenuse of 1. And remember when we did that, the x was the same thing as your cosine, and the y was the same thing as your sine. And remember, that's only if your hypotenuse equals 1, only if you're on a unit circle. But here we're going to assume we are. Now, Pythagorean's identity says that a squared plus b squared equals c squared. If I were to sub this out, I could say that a is the same thing as your sine of theta, b is the same thing as your cosine of theta, and c is your 1. And simplified, that is sine squared theta plus cosine squared theta equals 1. That right there is a Pythagorean identity. So I'll put it over here, because I'm going to do some more playing there on the right. Because like I said, there are three of these identities. So I can take my original function, and I can choose to divide it by, say, sine squared everywhere. And when I do that, I see that here it simplifies to 1 plus, now remember, cosine squared over sine squared was the same thing as cotangent, so that's a cotangent squared. And remember, 1 over sine was the same thing as a cosecant. So this is going to be cosecant squared. So that's your second Pythagorean identity. And if I had chosen instead to take my original sine squared theta plus cosine squared theta equals 1 and divide everything by cosine squared instead, sorry, that last one's kind of sloppy. My sine over my cosine, remember, was the same thing as tangent. So that's a tangent squared. Cosine over cosine is 1. And 1 over cosine squared from up here is the same thing as secant. So that's equal to secant squared. Alright, so when you have these functions, you can do something called verifying trig identities, and you can do a lot of playing with them. Now, I will point out here, I'm going to give you, I think this paper itself. There's many similar PDFs to what you see here that you can find all over the internet. What I taught you was the reciprocal, quotient, and Pythagorean. There are many other identities that we're not going to get to today. I'll get to some of them this week, but seeing as how you only have 2 lessons left after this for the rest of the year, I'm really not going to go through all of them this year. Okay, so I want to focus on verifying identities first. Let's just go ahead and get a new sheet. Let's not save. And I'm pulling my problems just from a worksheet that I found online. And our goal is we need to be able to prove that the left does equal the right. Okay, so my first problem, let me get this set up because that's, there we go, that should be good. I'm going to want to give myself plenty of room. And I've got secant of x minus tangent of x sine of x equals 1 over secant of x. So, to verify an identity, what you need to do, a couple steps. First thing, only play with one side of the equation at a time. Number 2, and this is the most important thing, this is not, okay, I just called it an equation, but it's not going to be treated like an equation. You never move anything across the equal sign. Never, ever, 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 ever. You're going to pick one side and play with it, and then see if you can get it to look like the other side. At most, you might need to play with them each, but you play with them each separately until they both equal the same thing. So, and then just some hints. You're going to want to look for cases that use the Pythagorean identity. Because that is very, very commonly used when you're verifying identities. And then the second hint is, when in doubt, rewrite all trig functions as sines and cosines. And so remember, when I say that, I had shown you the identity page, which I've already misplaced for myself. Here we go. So when I say that, notice that every function here, your sine obviously can be written as a sine. Cosine can be written as a cosine. Cosecant can be written as 1 over sine. Secant can be written as 1 over cosine. Tangent can be written as sine over cosine. Cotangent can be written as cosine over sine. You can write every function so it's only using sines and cosines, and sometimes that is a helpful step in solving the problem. Okay, so going back to my original problem. I want to demonstrate for you how to solve a problem like this. And I'm going to do several problems just because I know the more problems you see, the easier it is to get. Now here is what's frustrating for a lot of students is, unlike what you're used to with equations, there's no solving it like an ogre. That just doesn't work here. And most students, that's what they want math to be. I like with identities, I like to compare it to how many ways can I travel from the school to my house. And there might be one or two ways that I prefer, but realistically there's almost an infinite number of ways that I can travel from the school building to my home. I could go through and visit my parents in Missouri on the way back if I wanted to. There's no limit. So some methods will be a little bit longer, some will be shorter, some will be a little more difficult, just depends. But realistically, they all get you there, and that's really all I care about with identities. So, another hint that I didn't tell you up front is pick the more complicated side. Right now what I see is the left side is more complicated. It's easier to play with the more complicated side and make it simpler than try to complicate something in the right way. Because there's always so many ways you can complicate a problem. So what I'm going to do, here's what I do. I write down first which side I'm dealing with. So I'm going to start with the left. And I write down the problem exactly, because if you start trying to change it right away, you're probably going to make mistakes. Okay, so when I look at this function, I think that what I want to do here is change everything to sines and cosines first. That's what stands out to me. So your secant, remember, was the same thing as 1 over cosine. And your tangent function was sine over cosine. And then, of course, just your sine function here. Now, I only want to change one thing at a time. Now, or I don't want to start combining things in one step as well. Changing the two functions at once, that's not that bad. But trying to do any more steps in one line is really going to cause you grief. Alright, now what I see here is ultimately I want to be in one fraction. And what I like about this already is I see that I've got a common denominator already. That means I can add them together. Now I'm going to do one more step before I add them together, and that is I'm going to make my two fractions that I'm multiplying together into one fraction. So I get 1 over cosine of x minus sine times sine is sine squared all over cosine of x. And again, since I have a common denominator, it is a legal move to put them into the same fraction. Remember, with fractions, you add or subtract whatever you're doing. The numerators, the top, but the denominator, the bottom, just stays the way it was before. Okay, now 1 minus cosine, or 1 minus sine. That looks to me like a Pythagorean identity, because remember we said that sine squared theta plus cosine squared theta is equal to 1. I could rearrange this. This is a completely illegal move. Now here you can move things across the equal sign when you're using a proven identity, but when you're in the process of proving an identity, it's not allowed. Okay, so I know that cosine squared is the same thing as 1 minus sine squared, which is perfect because that's what I've got. So I replace that 1 minus sine squared with a cosine squared. And since this is cosine times cosine over cosine, one of my cosine sets will cancel, and I get cosine, which, according to my reciprocal identities, is the same thing as 1 over secant of x. Okay, so how are you feeling so far? I don't expect you to walk through it nearly as fast as I have. One big thing about identities is the more you practice them, the faster you'll be. And I've been practicing them for about as long as you've been alive. But what I do want is, I don't want to skip over this section, just because in a Math 1060 class, this is where probably enough of the confusions lie. That, remember, I think any subject you learn is easier if you see it first in high school. And I'm hoping that's still true from this distance learning, because we can meet during my office hours, or meet one-on-one whenever it works for you, and go through these things. But I'd like to be there to hold your hand a little bit with these, instead of just making you wait till you're in a 1060 class. And what I'm going to do over the course of a week, your college professors will do in just like a class period. Okay, so let's do another problem. And again, I'm just pulling from that worksheet I showed you earlier. And I don't have these prepped ahead of time, by the way. I'm just kind of going, cosecant of x, and I'm relying on the practice I've had with these. There are times even for me that I have to pause and restart the problem because I made an incorrect step somewhere. But I've got faith that I'm going to give you some problems that won't be too complicated. Okay, now on this one I think I'm going to surprise you, because I'm going to say that this is the more complicated side. And let me tell you why. It's because I have two terms. Here, technically they're all in the same fraction, so technically I would consider it one term. And having that extra term, to me, that's the thing that I want to play with. Even though the fraction on the left seems a little bit more complicated, to me the right side is the more complicated. Oh, and there was something I forgot to do up here. One thing that I do like to do is make a little note at the end once I've proven it to say that yes, the left side equals the right side. I'll do that for this problem here as I go. So I tell myself I'm starting with the right side, and I rewrite what that right side is. And I'm going to lean on the idea of let's change everything to the sine and cosine form. So cosecant from back on the proofs that we showed you, which these ones right here. Maybe I'll do a split screen here so you guys can see those proofs as I go. Okay, so that cosecant was right here. It was 1 over sine. And the cotangent was, I'm going to use just the one that was just cosines and sines. It was cosine over sine. And again, check it out. I love this because they have the common denominator. And hopefully you can see what's happening with the numerator compared to up here already. But I'm going to go ahead and add them together. Your numerator gets added. Your denominator stays alone, but only if they're already the same thing. And bam, already. Oh, somewhere along the lines, though, I did change my thetas to x's. It is an innocent mistake on my part, but because we use them as two different variables, you do want to be consistent about your variables as you go through the problem. But I can see here that I got the left side to equal the right side, so my identity was verified. Okay, let's do another one. Get my blank sheet. Let's see, the next problem on that worksheet looks like this. Alright, now I think on this one we definitely would agree which the more complicated side is. I think we both would agree that in this case it's the left side again. So rewrite the problem. And looking at the problem, I think this is going to be another one where I'm going to first step change everything to sines and cosines. I'm not saying you always have to do that, but I'm just, when I gave that as a hint, it really is a very useful step in many of the problems, and especially if you get stuck, is a good place to turn to. So we've got sine of theta over cosine of theta is the same thing as tangent, and cosine of theta over sine of theta is the same as cotangent. And if I clean this up just a little bit, I now have sine of theta over cosine of theta all over sine of theta cosine of theta plus cosine of theta sine of theta. Now, it might be tempting to cross out the sine theta over cosine theta, one on top, one on bottom, but because you have this other one on the bottom that's not a legal move, what you're going to want to do instead, what looks to me is we have currently these two terms on the bottom. We want to combine like terms, but we can't until they have the same denominator. So what I'm going to do is I'm going to multiply this term by cosine over cosine, because then I'll have sine times cosine on the bottom. And I'm going to multiply this term by sine over sine, so that again, this sine cosine on the bottom gives me the same denominator. Now here's the part I know a lot of you won't like, is doing trig identities will take some extra writing, most definitely. You can't solve typically in just one or two lines. Sine theta, cosine theta. Alright, so now I can put those fractions together. I'm going to expand this out just a little, so I can do that over here. Alright, so I end up with sine squared plus cosine squared all over sine times cosine. And what's really great about that is this is the Pythagorean identity. Sine squared plus cosine squared equals 1. So I can say that that's the same thing as sine theta over cosine of theta all over 1 over the sine of theta times the cosine of theta. Okay. And if you do get stuck on these steps, please do watch the video through again on the parts you're getting stuck on, and then contact me and let me know what parts you might still be stuck on. But at this point, I've got a fraction over a fraction. I never like that. We have to think about my little sister. Remember, my feet and my head stay where they normally do, but hers, the second one, gets flipped. And as I do that, I can see I've got a cosine on the downstairs and a cosine on the upstairs. And it simplifies to sine squared over 1, which is just sine squared. And let me see, I think that's what the right equaled. Yep. So I started with the left. Through a series of legal and mathematical moves, I got to the right, so I proved that the left does in fact equal the right. Okay, let's do yet another one. Okay, another one just from that worksheet that I found online. I think this one would be another good one to go ahead and put just in sines and cosines and see what happens. So secant is 1 over cosine all over cosine minus tangent, and you can see it on the right side of the screen. Tangent is the same thing as sine over cosine. Cotangent is the same thing as cosine over sine. And I should have established, actually, look at me breaking my own rules. I should have written down the more complicated side first. But I'm going to cheat because I'm using technology. That I am starting with the left side, which was secant theta over cosine theta minus tangent theta over cotangent theta. That left side is definitely more complicated. Alright, so I've got some cleaning up on my fractions to do before I can start even thinking about combining them. So I'm going to use my little sister rule. Notice I gave my little sister legs here on this part of the problem. And you leave me alone, but you flip my sister upside down. And you leave me, the first one, alone, but you flip my little sister upside down. And what I love about this is I can already see I'm going to have common denominators just come out of this. We've got a cosine squared here. We have a sine squared over a cosine squared here. And since they already have a common denominator, that's 1 minus sine squared theta over cosine squared theta. And remember, when I had 1 equals sine squared theta plus cosine squared theta, just like before, if I want a 1 minus something, in this case it is the sine function again, won't always be, but that's what it is here, then I can see that 1 minus sine squared theta is the same thing as cosine squared, of theta. So I can substitute out what's on top here for a cosine squared theta. And check it out, you got the same thing on top and on bottom. We get 1, which was what the right side equaled. So again, we proved that the left side equaled the right side. Okay. I think I'm going to pause there. Mostly because this video is already half an hour long. And I'm going to give you some of these problems for today. You are going to see more of them in your homework on Wednesday, the one that I assign on Wednesday. And like I said, I wanted to at least get started with identities just because I don't want you to wait until you're in college and get blindsided by them. Okay, so your homework assignment is on Alex. It's called Verifying Trig Identities. Let me know if you need any help. Please do start this assignment earlier rather than later. And I will talk to you this week. I hope you're having a great week.